All right, physics teachers are awesome. Reaction video number 100. Today looks like some RC circuit stuff. Let's see, with batteries. So I don't think we're doing AC stuff yet. Well, we'll see how it goes.
So where do the RC circuit equations come from? So I'm going to take a look at a charging capacitor, and I've written down some important equations to start with. Voltage across the resistor given by Ohm's law, the relationship between charge on a capacitor and the voltage of the capacitor, our time constant, which is just R times C, that characterizes how long things take to charge up, though it is.
You know, it's interesting. I think that every time I see RC and think about how miraculous it is that its units are seconds or time, it's like, oh, how does that happen? But of course, I always think of it as capacitance as having really have timing built into it. But again, you know, you see this, you see charge over voltage, you think, okay, that's a weirdo unit. And of course, resistance is a weirdo unit we've never heard of. And all of a sudden, you just multiply the two together and bam, just ends up being time. So I always think that's really, really cool. And of course, it's really convenient to understand what's going to be happening with you know, charging up or discharging this circuit.
Isn't like the limit. It's not fully charged at this time. Remember, that has to do with like the 63% and 37% from the equations. The maximum charge that's ever going to be on the battery is the maximum voltage we can get, which is the voltage of the battery. And that happens when there's no current, so there's no voltage drop across the resistor. Well, the max current will then, or the max charge will then be the voltage of the battery times the capacitance of the capacitor. Just start from this equation. And then finally, the maximum current will happen when all of the voltage drop is across the resistor and none of it's across the capacitor because there's no charge on the capacitor.
So I really love this setup, you know, talking about some very, very characteristic features of this, right? The biggest the charge can ever get, the biggest the current can ever get. It's super, super useful, especially as you contemplate, I don't know if she'll get to it, but, you know, plotting some of these functions, and they all have these sort of asymptotes, right, where they're just going to get up, either start at their max or they're going to end up at their max. And it's really, really helpful to have this this information here. A quick comment about the physical setup of this video. Obviously, it's a camera pointing straight down, and you can see when you look at the shadows of her hand. Let's see if we can. So we're at 106. Go back here to, we'll just go right there. Nope. Let's go back again. Come on. Let's find her hand somewhere. We'll get in here somewhere. There we go. So, so her hand is here. There's clearly a light that's below the screen to produce this quite dark shadow, but it's an array of lights. There's at least 3. So it's really well lit. And then the other thing that I'm noticing is that there's not this defocusing that happens, right? So when her hand is there, it's not focusing on the top of her hand. It seems to be keeping the whiteboard really, really well in focus. I think that's really great. What did I say? 106? We'll go to 105. All right. Oh, here's another perfect example of the shadow. All right, here we go.
Charge on the capacitor. So this max current is also the initial current, and it's the voltage of the battery divided by the resistance. And that is coming from Ohm's law here. Okay, so starting there, and using the loop rule, we will have a gain in voltage across the battery, and then we will drop in voltage across the resistor, and drop in voltage across the capacitor.
Cool.
And that has to all add up to 0, as we always get for the loop rule.
Awesome.
Now let's go ahead and sub in what these two are. So the voltage of the battery minus the voltage drop across the resistor, that's current times the resistance, minus the voltage drop across the capacitor, that's going to be the charge on the capacitor divided by the capacitance. And then what?
Just wanted to comment quickly on a couple of things. So first of all, using this lowercase q here compared to the capital Q, I do actually like it because this Q max, sometimes I can be really, really lazy and forget to type the max part. And so lowercase q helps me remember that it's very much a time-dependent quantity. What else is a time-dependent quantity? This isn't, this isn't, this is, and this isn't. So we really only have 2. And then, of course, the other big thing about RC circuits is that right now the students are like, oh my God, there's just so many unknowns. I don't know what the heck is going on. And so we clearly need one more relationship, and it tends to be the one between Q and I. And then once you have that, then you're ready to roll.
One final thing that I need to put in is the current
Here we go.
is the derivative of charge with respect to time.
Love it.
So I'm going to wipe that out and put in derivative of charge with respect to time. Okay, and now that I've got it written like this, everything that's a capital letter is a constant. Voltage of the battery, the resistance, and the capacitance. The things that may be changing, and in fact are changing, are the charge and time. And this here, now we've got a differential equation which we can solve, and we're going to solve it by separating out the variables. We're going to put all of the charge variables, including this guy and the derivative, the dq, on one side of the equation, and we're going to put the time on the other side of the equation.
So I just wanted to pause for a second and recognize that sometimes there's an extra sign that you put in here because you sort of stare at this and you're like, okay, well, if I'm going to call the current positive, then that means that charge is building up on here. But then later, when you take the battery out and you put in close the switch to with no battery, and it's discharging, all of a sudden, then this is a negative thing, and yet you would still call it a positive current. So it's really, really interesting to watch and see when that comes up. I'm super sensitive to it because, frankly, in front of students, I'll screw it up every time. For this case, if we assume that this thing starts uncharged and we close the switch and we get this going, then we would think of current is flowing this way. We'll call that the positive. So let's call clockwise positive, and then charge would be building up, so it would be positive. And so this is absolutely the right way to do it for a charging capacitor. And it kind of sucks that for a discharging capacitor, depending on how you set it up, it'll feel like suddenly this equation doesn't work anymore, and you have to have this extra negative sign. And so what I ask of my students is just just say it out loud. What's happening? Is the capacitor charging or not? Do you want to think of that as a positive derivative or a negative derivative? And then which way are you going to call positive current? So it can be really, really tricky for this first case, right? The students don't even know that there's some trickiness. And so I'm just thinking ahead. And so it's really interesting to see how that might show up. I don't know if this is going to get there, but it's a subtlety that I think about a lot.
And then we'll be able to integrate it. All right, so first I'm going to clean things up by just multiplying the whole equation by c. I'll just move this r out front so we know we're not going to take the derivative of that with respect to time. There we go. Now I'm going to move all of this over here. So I'll have the voltage of the battery times capacitance. Oh look, that's Q max.
Awesome.
Minus Q equals RC dQ dt. Open RC, that's the time constant.
Nice.
Okay, and now I'm just going to multiply this by dt and that by dt. This looks a little sketchy, but it is actually 100% fine. I'm not being very careful about showing when I'm taking a limit. And then I'm going to divide this on both sides of the equation. So over here I'll have dt, and over on the other side I'll have RC dQ over the voltage of the battery times C minus Q. Okay, so now I've got T on one side and only Q on the other side, so I've separated out my two variables. And next, now we can integrate, but we have to be a little bit careful about the limits. So Q and T are now integration variables, and if I...
That was cool, adding those primes to turn them just into integration variables. I like that, and my guess is that's something that her students are quite used to. It's really, really interesting that the students immediately will recognize dq over q as natural log, but they don't always recognize, wait a minute, there's this extra constant, I'm freaking out, right? And so the question is, and I deal with this when I talk with my mathematician buddies a lot, they're sort of instinct for these things is so much more finely honed. They're just like, oh, yep, got it done. And our students sometimes have to be encouraged, okay, we'll just do a variable substitution, get it into the form that you feel like you know. And it's really, really interesting to think about how useful is it to encourage students to develop that instinct deeper than it already is. I'll be honest, for myself, the only thing I remember is dq over q is going to give me some natural log stuff, and I just know that, oh, okay, I'll bet you I can do a variable substitution to get this to look like that, as opposed to just saying, oh, I know what this is immediately and writing it down. So I'm curious to see how she does that.
I go from my 0 to the initial time. I can do something similar over here, but over here my integration variable is going to be q, and the limits should be the charge down here. How much charge is on the capacitor when t equals 0? Well, if we're charging the capacitor, it starts with no charge.
Awesome.
So we're going to put in 0. And I want to emphasize that my integration variable q is 0 when t prime is 0. So these two limits are the charge and the time at the same point.
Nice.
And then up here, I'm going to go to q, and that's going to be whatever charge I've got when time is equal to t. So the top limit is my charge is q when my time is t. And that's really important. We're doing different variables, but we're matching the limits here.
Right.
Okay, so then if I do that, this side just integrates to time. RC is a constant. It doesn't depend on what's going on in here. And this guy, I'm integrating like 1 over my variable, so that's going to be a log. And q has a negative in front of it, so I'm going to negative here, and that'll be negative ln of VBC minus q prime, and we're going to evaluate q prime from 0 to q.
Huh.
All right, so now I'm going to erase.
So interesting, right? So we don't know what sort of set of instincts her students have, and so being able to just write that down as an immediate natural log, that's great, right? So if the students have that in their bag, then you can skip the step of doing the variable substitution, and so it's really interesting to think about what really matters here. So what we're going for is the fact that it's somehow exponential. This right here is kind of the big idea that we go from, well, oh, this is old stuff, I know this Kirchhoff's law stuff, to, oh, wow, there's this really cool idea, and then bam, it's just some integration after that to get there. So that was really cool. I think I'm actually going to pause here. We're about 12 minutes already. So I think that I really, really liked how she set up the really important variables that were going to be coming. I really, really loved using the old stuff, and then, oh my gosh, that whole conversation about the limits I thought was really, really fantastic. All right, everybody. Well, hey, have a great day, and remember, physics teachers are awesome.